interval A to B is this guy. Okay? What would be the actual value of this if I compute this through the partition? The actual value of this guy is going to be equal to the sum actually, I mean, if you think about it. So it would be the sum of I equal to 1 to n of these increments. Huh?
ds.
ds, but okay, you can say it's alpha of ti minus alpha of ti minus 1n. So this would be the length of it. Okay, so what I want essentially is that as n goes to infinity, this guy is going to converge to this guy. ठीक है? ठीक है?
Chain entry as 0.
Shall we do it or shall I leave it? Because we did this Stokastas there. So what there was something similar actually, if you remember. We proved something similar in functional analysis. Okay, but like I can give you a sketch, how does it work? It's not a big deal. ठीक है?
Sir, partition P का use हुई sir.
कहाँ पर?
इसमें.
It's here. So you are computing, the value of the curves on, each of the segment actually. So I'm saying that okay, on this interval, take this small piece, so select all these increments, okay, and sum them all. Their sum is going to give you the approximation of the length of the curve. Okay? Is it that complicated?
सर अगर ये तब पॉसिबल होगा जब अल्फा प्रिजर्व कर लेंथ को.
क्या मतलब?
हम छोटे इंटरवल लेंगे तो वो लाजमी है मगर हम वो इंटरवल.
No, but think about it. No. Okay. We already know that tangents are a good way. So tangents are what? So tangents are the best linear approximation to a curve, in a small neighborhood basically. So this partition is pretty big at the moment actually. But if I, just slice it more and more actually, okay, then you're going to get what? So what you can say, okay, so what do you want to see this, for example? Okay. I think that this is not good. So I'm saying that take an arbitrary point from this interval, okay, and try to draw a tangent line on this actually. So I'm taking an arbitrary point from this interval and drawing a tangent line. And then taking an arbitrary point from this interval and drawing a tangent line, and so on and so forth. So for each sub-interval I'm drawing a tangent line, and then I'm saying that, okay, sum these all small segments, and then you get, what do you call, the length of the curve. I think it's not that strange out there.
Sir, we haven't used it.
Okay, here's the claim actually. If you don't understand, fine. If you think it could be counterintuitive, I think it's not that counterintuitive. I'm saying that this is a quantity, okay, which converges to this quantity and then goes to infinity. That's my task actually. Whether you believe the picture or not. It's fine. It's a Riemann sum actually. The magnitude of E is just a symbol actually. But this will allow me to, take my things to zero. If this guy goes to zero, then each of the increment is going to zero because each of the increment is smaller than this actually.
Sir, multiply by.
Let me formulate the theorem. Okay? Let me formulate the theorem. And then you will see it. You say, I can't see the derivative there, but we are forgetting the mean value theorem. We have a mean value theorem.
Multiply, divide, plus
We will use the mean value theorem. You?
हाँ
We have a mean value theorem. So why we did the mean value theorem? Just because of this actually that. Okay. How much time do we have? So what I'm going to do this. Okay, let's not get into the proof. Let me just, what I'm going to do that I'll write the proof on the page and I'll put it on LMS actually. So you can see it from there. So it's a pretty elementary proof actually. It's not that difficult. It's just, the 2 times application of mean value theorem and you can do it actually. Okay? So let's do some more kind of creative stuff. So what we have so far is we defined curves, examples of curve, we know what is length actually. So I would like to put 2 remarks. The key 2 remarks about the length of the curve. And these are the things that we proved in our multivariate calculus, so I'm not going to do it here actually. So I'm just recalling that we know, still remember. The length of the curve, okay, of curve is preserved by isometries in R3 or maybe in Rn actually. Okay? So length would not change if you apply any isometry on a curve actually, or if you compose them with any isometry. Okay? And what are the isometries in R3?
distance preserving distance meter
And
preserving
what are the examples of isometries that
अच्छा
Linear length
सर नाम में से जो
linear curve
what mean by linear curve?
from R to 1.
Translations.
translation yes
So the translation is an example. Translation is an example of isometry. So if you translate it, okay, so it's like my curve is here in this space. Okay, so if I translate it, I put it here, and maybe I put it here, it's not going to change the length of the curve actually. Okay? So it's preserved under
rotation
huh?
rotation
And then the rotation actually.
Translation and rotation.
You have just did a course of group therapy. You must have
Symmetry.
seen these examples that the collection of translations and rotations forms a group actually. Okay. Or you can have a combo of both actually. So you translate and rotate at the same time actually. Okay. So it would still, does not change the length of the curve. Okay. It would be a good exercise to prove. What do we mean by, translating a curve actually? What I need to do. So it's like, I have a curve alpha of t. How can I translate it? So add a vector into it, a constant vector into it. So this is, what do you call, a new vector. The alpha bar of t. You will see that the length of alpha bar is same as the length of alpha. Okay? And what would be the meaning of rotation actually? So I have this alpha of t and multiply it with the rotation matrix actually. Okay? And you get maybe alpha star of t, something like that. Okay? So A is a rotation matrix. I hope that you guys know that what is the rotation matrix in R3. Okay? and then compute the length of this alpha star, it would turn out to be the same as the length of alpha of theta. Okay? So the translations and notations are not changing, are making any change in, what do you call curve. Okay? So that's another. The next thing that I would like to do comment is something that we also did in multivariate class, that the length of the curve is independent of choice of parameterization. Okay? So, for example, if a curve, so for the circle we saw the two parameterization actually. So if you want to compute the length of the curve, in other words, length of the circle, in other words, the parameter of the circle, okay, then it would be the same 2 pi r, whether you calculate it with cos t sin t or maybe the other formula that we give. It's not going to change. Okay? And we prove the theorem as well in multivariate calculus. So recall these things actually. Okay? The length of curve is dependent of choice of parameterization. Okay. By the way, we called paths to the curves in multivariate code, but they are same thing. Okay, we are happy with this. So what we have so far, we defined alpha, we did examples, we said that, I'm going to put what we call the proof of thing that, this justifies the length of the curves, and the length of the curve is unaffected by isometries in R3, VRN, and the choice of the parameterization that depends on that. So it could be anything. More, and let's see at what we are getting at.